So this is a solution to tutorial 5, which is based on the content from chapter 4. So for this question we have a mass spring system, so no damping, and it's got the differential equation of motion mx double dot plus kx equals some forcing function, which is the function of time. And this forcing function in this particular question could be represented as a periodic signal using the Fourier series, and that's given there in the expression here. Okay, so we've got the sum from n equals 2 to infinity of an cosine n pi t upon 2 for n being an even number. And an is given as 16 divided by n squared pi squared. X is a displacement. So the question asks, what is the trial function we need to use? What is my solution for x of n? And what is the steady state solution x of t? So let's work this out. And before we do so, we're just going to state that the nth term of the forcing function Fn equals an cosine of omega n t, where omega n is n pi upon 2. Okay, so you can see that this bit here, this is cosine omega n t, where omega n is n pi upon 2. So there's our Fn, and what this process requires us to do is to find xn for this solution, and then we add them up using the sum that we've got here to get the final solution. So the trial function we need to use. Okay, well this is just from the theory. The trial function we need to use from the theory xn equals alpha cosine omega n t plus beta sine omega n t, where alpha and beta are arbitrary constants that we're going to find in the next step. Part B says what is our value for x of n, so we have to go through the process of substituting our trial function into our solution and working out what those arbitrary constants are. So for that we need to, so we've got our xn, which is our particular integral. We need to find the second derivative of the trial function, and that's straightforward. Xn double dot equals minus omega n squared, and then we have basically the same trial function. So we substitute this into the equation of motion. Substitute. So we substitute this into equation of motion. So we've got minus m omega n squared alpha cosine omega nt plus beta sine omega nt plus k alpha cosine omega nt plus beta sine omega nt equals an cosine omega nt, and that comes from that equation there. So let's group the common terms. So we've got alpha k minus m omega n squared times by cosine omega nt, okay, plus beta k minus m omega n squared times by sine omega nt equals an cosine omega nt. So it's quite clear that alpha k minus m omega n squared equals an, and so alpha must be an divided by k minus m omega n squared. Beta k minus m omega n squared must be 0, and beta must therefore be 0. So the nth solution x of n, so we basically substitute these two things into this equation, okay, equals an over k minus m omega n squared cosine of omega n t. And so if we substitute in our 16, so if we substitute in our a of n term, we've got 16 divided by n squared pi squared, okay, then we've got cosine omega n t divided by k minus m omega n squared. There's our nth solution. And so for part C, what's the complete solution? Well, x of t is the sum from n equals 2 to infinity, where n is even, of x of n. And so that's the sum n equals 2 to infinity, where n is even, of 16 divided by pi squared n squared cosine omega n t divided by k minus m omega n squared. And clearly any non-n terms can come outside the sum. Pi squared n equals 2 to infinity, where n is even. We've got cosine over n squared k minus m omega n squared, where omega n equals n pi upon 2. There is our solution. It's important not to forget this term here. Okay, if you forgot that, then there'd be a mark lost probably for this sort of thing, because you've got to specify what an omega n is. Alternatively, you could insert that into the equation and leave n pi upon 2 wherever you see an omega n.